With a linear actuator, where would you most likely find, or what type would you most likely find to be used in a trimming device out of all of those? Yeah, absolutely, linear actuators. Right, generators. Now, we are comfortable with the concept, are we, that if we put a current through a wire, then we've got a magnetic field. If we put that wire through a field, we're actually going to get current, which was Faraday's giant leap of faith, wasn't it, from a little video clip. It reverses the function of a motor. Basically, Faraday worked out, didn't he, that if we put current into an armature, we can make it turn, but if we turn the armature with a prime mover, we produce current, or we produce electricity. And that's at the basis of it. Now, because we've got those two functions in essentially very similar devices, it enables us to have some significant weight savings on certain types of aircraft, where a starter motor can be used to turn an engine to start it, and then once it's running, it can then be turned itself as a generator. So one component as a starter generator. Seems like a damn fine way ahead. Fleming's right-hand rule, which genuinely I don't believe you need to understand any more than the fact that the right-hand rule is for generators and the left-hand rule is for motors. Okay, simple. So the layout is exactly the same. This time though we're going to turn this and that will then produce current rather than putting current through there and it will turn the armature. Simple as that. Now the field coil itself, these field coils, the field windings, they can be separately excited from the battery, because clearly that won't be a magnet until we've got some current flowing in there, will it? Where are we going to get that current from if the generator's not actually generating? So we need to first excite the magnets with a current from a battery that's externally or separately excited. Some generators are self-excited, that uses residual magnetism, sometimes just a small pair of permanent magnets to just get the whole process started, and then once it's generating it drives its own field coils. What do you say, H? Second?
Number two.
Number two, yeah, exactly that. EMF induced in the conductor. Now, just like with the motors, generators can be wound in different fashions, and it has a different effect. If we have a shunt field coil, so you've got your generator there, your field coil is actually in parallel, it's a shunt coil, with the main circuit resistances. Now what happens is the circuit resistance decreases when we put loads on. We saw that, didn't we? The more resistors we put on it, it actually decreases the total resistance. So the effect of that is that the current increases. That means that the current through the shunt coil also will be decreasing because of it's in parallel, and the voltage output reduces. Suffice to say, shunt field coil, you start at peak and you drop off under load. Not really desirable. The opposite happens with a series field coil. With a series field coil, an increase in circuit current gives you an increase in field current. The load increases, the field current increases, vicious circle. Voltage increases. So that one starts at nothing and picks up to peak. Again, not ideal. The compromise would be to have a compound wound generator where you've got basically 100% of the output across the whole load, and that is the most common to find series and shunt coils in a generator. It gives you a stable output near to 100% all the way across, but not constant voltage, so we might still need a voltage regulator. Voltage regulation, the old-fashioned approach is the carbon pile. Basically you've got a stack of carbon discs with a spring on them, and the closer they are together, if they're compressed, the resistance decreases, better contact. If they're relaxed, the resistance increases. So we use that, look. Generator voltage increases, run that one from the start again, actually, might be easier. Okay, the generator voltage increases. The effect of that is that the voltage coil here becomes more powerful, and that magnetises here, so this is like a solenoid. The compression on that is relaxed, which increases the resistance, which decreases the current through the excitation coil, which in turn decreases the output of the generator. Simple. Old-fashioned, still works. This is a slightly different one. This is a vibrating contact regulator. Once again, generator voltage increases, the voltage coil here becomes more powerful. The points will be pulled open, like this relay here, which increases the resistance. That decreases the current through the excitation coil, which decreases the generator voltage, and the points close. Now that's happening 50 to 200 times a second in a vibrating contact voltage regulator. Again, quite efficient, but because of the contact breaker points, the physical points, if you put high loads through them, you burn the points out in no time at all. So they're really only suitable in low current systems. If we've got two generators and we want them both to feed a common bus bar in a process called paralleling, parallel generators, they must be balanced to share the same bus bar. Otherwise, if you had this one chucking out 28 volts and this one chucking out 27, then that would try and drive that one back as a motor. The current, or the voltage output must be matched. And we achieve that with two carbon piles, so each one doing its own job there on managing the voltage output of that one, and this one doing the same thing for generator 2, but the equalising circuit is making sure that the averages between the twos remains the same. Same concept as a carbon pile, just two of them with a balanced circuit. Paralleling. Now it must be the voltage that's the same for paralleling. It gets much more complex when we get onto AC, but basically that's a fairly simple system. The modern approach is actually to separate the systems, as we will see. If we have a generator fault, we need a protection system. What happens if we have a generator fault is it opens the generator field current relay, this one here, so we're not energising the field coil. If we're not energising the field coil, we're not producing electricity, are we? We'll also kick the generator offline from the buzz bar, and we'll be told about it with both the amps and with the generator offline indication somewhere in the cockpit. So at this point, with a single generator system, if we lose that gen, it stops generating, so in case it's an internal fault, we don't want a fire, and it also kicks it off from the buzz bar. So now the only thing powering the DC bus is the battery. We could also find ourselves in a situation where if the generator itself was not producing sufficient output, remember we needed 28 volts output to charge a 24 volt battery, otherwise the battery will win. So what we have is a reverse current relay here, and typically if the battery was 24 volts and the generator was 28, that reverse current would cut out at about 27 volts. Otherwise, the battery would try to turn the generator as a motor. Remember, it's the same principle for generator and motor. So if we don't put out more than 27 volts, it will kick itself off to protect. Otherwise, the battery voltage, instead of powering emergency services on the aircraft, would be busy trying to turn that generator as a motor. We can't allow that to happen. Principles generally applying to both DC and AC that we have priority of services. Vital services on DC are those provided from the battery bus, sometimes called the hot bus or the direct bus. Essential services are those required for safe flight in an emergency, and non-essential services are those which we can safely shed or turn off in an emergency. Now I mentioned that the modern approach was to split the system, which avoids the problem with paralleling. This is a typical split system, and like most people, when you look at that, your eyes start to turn up into the back of your head. You go, oh no, another one of these. Just follow the diagram through, alright? Let's have a look. What have we got here? We've got two generators, number 1 and 2. They are not connected across the aircraft. The number 1 gen is powering the number 1 DC bus bar. The number 2 gen is powering the number 2 DC bus bar. On the number 1 DC bus bar, we can connect external power and the bus logic circuits on the aircraft. When you plug in the external power, we'll normally close that one as well, so that you're powering all the services in the aircraft from external DC. But in normal use, that remains open, and obviously you don't fly around with anything plugged in there. Okay, staying with DC then, the number 1 DC bus provides essential DC services on that bus bar, and from the number 2 bus bar we are providing non-essential DC. Coming further down from the DC bus to the battery switch takes us to the battery bus bar. You remember that can also be called the hot bus or the back bus. From that we connect the battery and the Viper DC services. So in the event of both generators being offline, okay, that bus bar will be powering the DC services because they're hardwired direct to battery. Some aircraft also require some AC services. If they do, and you've not got AC generation on board, then DC generation from the number 1 bus through an inverter provides AC to the essential AC bus bar, and the number 2 through an inverter to the non-essential AC bus bar. So far, all fine and dandy. So we've got 3 sources of DC there, battery, 2 generators, and we've got 2 means of converting or inverting DC to AC across there. So now let's look what happens if we lose a generator in flight. Okay, if the number 1 Jenny should trip off in flight, the generator control breaker will come out, the bus tie bar will normally automatically close. So now the number 2 generator is powering both bus bars. Now it may not have sufficient power to do that for a finite period of time. So we may well find ourselves having to shed some of these non-essential services in a process called load shedding until we get to a point where the generator output is providing sufficient for our needs. So in normal use on a split system, the bus tie remains open. Any questions on that diagram? Pretty straightforward, isn't it? Okay. Protection devices. We need some means of making sure that we don't set the aircraft on fire if we end up with too much current going down a cable or a conductor. Remember, heat is generated, so we need circuit breakers. Now, circuit breakers are of 2 main types, the bimetallic type or the magnetic type. Magnetic ones are quicker. Bimetallic ones need to heat up before they trip. So a magnetic circuit breaker will jump out straight away. Bimetallic, it will start to overheat and then go, oh okay, I'll kick out now then. Normal rule is they can be reset once only in flight, as a general rule. Circuit breaker panel looks something like that, and basically all you've got in it is a whole bunch of these things. Right? Push in, circuit made, pull out, circuit broken. Simple as that. Jim? The other type of protection device commonly used are fuses. Now fuses are normally a zinc alloy, and they have a wasted section in them, which is to say that what you've got is, there's your strip of zinc alloy, and all you have is a narrow section, which is the bit that's designed to fail. Because if current flowing through there, if there's too much of it, as it gets through that point, that will heat up and that will just fail through there. All seen them in our cars, I'm sure. Look at the little blade fuse, you hold it up to the light, you can see if it's popped or not, if it's blown.
Just one question for the circuit breakers. You said like bimetallic and magnetic, there is a difference?
Yes.
There is one with
Yes.
Which one?
Bimetallic is slower because that has to first heat up and then the two metals will spring apart. The magnetic is instant. Okay. With fuses, you'd normally carry 10% of the fuses in the aircraft spare. And again, the rule is normally that they're to be replaced once only in flight. And you can see the little zinc alloy areas in this one here. Look, you can see there's a thicker section there, then there's a thin section. So that's the weak link. That's designed to fail. The one that's coming around the room now, look, push in, circuit breaker closed, normal operation, circuit breaker popped, there's a supply in but no supply out. We've just turned it off, it's a switch. Now the circuit breakers themselves can be fitted, or normally are fitted close to the power source, and they can be colour coded. Now if they're colour coded, a red circuit breaker may need to be manually reset in flight, and if they're yellow or white, it indicates that they can be pulled to isolate a service, to turn a service off. A third type is a trip-free breaker. Now a trip-free breaker is one that cannot be held in to remake a circuit. Once it's popped, it will not allow it to be re-engaged. Coming on the horizon, but not yet examined, are virtual circuit breakers. So if you sort of don't do your exam for a while and come back, you may find yourself asked about virtual circuit breakers. This is really only for interest now. For the heli boys, this one's from Augusta 169. And basically on the touch screen interface that you've got with the aircraft systems, you've got pages and pages of circuit breakers. They're solid state breakers, all right? They're not physical breakers in the sense that we would understand them. And literally, they've gone for a nice, comfortable depiction of a circuit breaker that we all know and love, but all you're doing is just turning that switch on or off remotely. You're not actually touching a circuit breaker there. As you can see there, you can have them failed, tripped, out or in. A lot more information as well, because as you've got on the circuit breaker panel of a fixed-wing aircraft, tiny little lettering telling you which circuit breaker that is and what service is. This is telling you that that's the comms, audio management unit on the normal. Its subsystem is comms. It's on bus bar main 2 and it's rated at 1.1 amps. So a lot of information right there. Warning lights generally, just as a reminder, because they can pop up in AGK, warning lights standard really, red, amber, green for warnings, cautions and advisories. Blue is used for things that are in transition. So if you've got a fuel valve, for example, in transition, it will show as blue. And normally white would be for information. So for example, that your ground power's on. We touched on this in the instruments package as well. The convention should be for new aircraft is that the switches are forward on the centre console for on, up on the panel for on, and back on the roof for on. So basically, if you were to bring your hand from up there and do that, you've turned everything on. It's the other way around on most helicopters, just to confuse people who are doing two types. We looked at these as well the other day on basic construction, reminding ourselves that the bonding is necessary to maintain the same potential difference through the aircraft. And finally on DC, we can have this sort of braided wire shield, like a coax cable that you've got for your television. And the current carrying core sits through there. We've then got layers of insulation and a braided wire shield. It stops it humming, it stops the current going through it, making hum on radios and intercoms and stuff like that. Screen bleeds. DC. Simple. Yeah?
You mean cables with a shield or for DC?
Sorry?
Just the slide before. Even for DC current, we need shielded wires?
They're commonly used in aircraft where there's a high current load to stop it making noise through the aircraft. You'll hear a hum through the headsets otherwise. Yeah. Okay. AC. Alternating current, if we're talking about direct current, we're only producing positive peaks on this side of the line. With an AC, we're producing positive and negative all the way. So, if we want to know the value of the voltage there, we can look at it on that graph or on an oscilloscope. We could see that the peaks are, 120 volts or whatever, and the minus peaks are 120 volts. There's a problem with that though. If we want to get a meaningful figure out of it, what is the problem with sine wave mathematics? What's the sum over time? The average is 0. And I can promise you, if you were to grab that end of the cable, it certainly would have volts in it, but an indication would be that there is nothing in there because the average is 0. So what we need is a means of giving us a useful, meaningful voltage reading. We use the root mean square method. Now, what we do, because the average voltage would be 0, no matter how high the peaks are or how low the troughs are, the average would still be 0. So it doesn't give us anything that we can usefully use. So, first we square the voltages, which gives us positive numbers across the board. We then average them together, and then we take the square root of them. So it's root mean square. That gives us an RMS voltage, which is not the same as peak voltage at all. It's actually, because of the mathematics of sine waves, it's 0.707 times the peak voltage. 707 shouldn't be a difficult number to remember for pilots. The RMS voltage would be said to have the same heating effect as the equivalent DC voltage. It's the same thermal value. For example, if you were to go and plug in at the wall over there, you would have 240 volts RMS coming out, root mean square voltage. But actually, it's 240 over 0.707, so the peak voltage would be 340 volts. But we all accept that what comes out the wall is 240 volts. You just check that figure, Jim, have you? Yeah. Does it come out right? Yeah. Thanks. Trust me, eh? Trust me, I'm with Bristol Ground School. Oh, no. Okay. Little video clip coming up on generation of AC electricity. It's done with a horrible American computer-generated voice, but the lessons it tells are quite good. I want you to take particular note of the fact that it doesn't matter whether you're going to rotate a magnet in a coil, or a magnet around a coil, or a coil around a coil. Either way, when you do it, you are producing electricity.
Alternators are the workhorse of the power generation industry. It is capable to generate AC power at a specified frequency. It is also called a synchronous generator. Electricity is produced in alternators by electromagnetic induction. To generate electricity in a coil, either the coil should rotate with respect to magnetic field, or a magnetic field should rotate with respect to the coil. In the case of alternator, the latter approach is used. Rotor and armature coils are the two main parts of an alternator. Rotor produces a rotating magnetic flux. Armature coils are stationary. And rotating magnetic flux associated with the rotor induces electricity in the armature coils. This kind of rotor, shown here, is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. Magnetic field produced around it would be as shown. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it at the same speed. Such revolving magnetic flux now intersects armature coils. which is fitted around the rotor. This will generate an alternating EMF across the windings. Here is a slowed-down version of rotor-stator interaction. For this 4-pole system, when the rotor turns half revolution, induced EMF takes one complete cycle. It can be easily established that frequency of induced EMF, rotor speed, and number of poles are connected through following relationship. It is clear that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase AC current, 2 more such armature coils, which are in 120-degree phase difference with the first, is put in the stator winding. Generally, one end of these 3 coils are star connected, and 3-phase electricity is drawn from the other ends. It is clear from this equation that in order to produce 60 Hz electricity, a 4-pole rotor should run at following RPM. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor, and it may fail mechanically over time. So salient pole rotors are generally having 10 to 20 poles, which demands lower RPM. Or salient pole rotors are used when the prime mover rotates at relatively lower RPM. Pole core is used to effectively transfer magnetic flux, and they are made with fairly thick steel lamina. Such insulated lamina reduces energy loss due to eddy current formation. Armature winding of 3-phase 12-pole system is shown here. A stator core is used to enhance magnetic flux transfer. DC current is supplied to rotor via a pair of slip rings.
See those on the thing that's coming down the room now.
DC current is supplied either from an external source or from a small DC generator, which is fitted on the same prime mover. Such alternators are called self-excited. With variation of load, generator terminal output voltage will vary. It is desired to keep the terminal voltage in a specified limit. An automatic voltage regulator helps in achieving this. Voltage regulation can be easily achieved by controlling the field current. If terminal voltage is below the desired limit, AVR increases the field current, thus the field strength. This will result in increase in terminal voltage. If terminal voltage is high, the reverse is done. Hope you have a nice introduction to working of alternators. Thank you.
Have a nice day. Okay. Good though. Very clear. Probably the best explanation I've seen of AC generation on animation. Okay, so comparing the two then, DC generators, yeah, we've got our standard split ring commutator, and what we're producing every time that goes through one rotation, it produces a peak of positive voltage. So it's positives all the way along the timeline in one direction, DC current. Alternator, because it's a slip ring rather than a split ring, the slip ring means it's a constant connection through there, and basically we're producing positive and negative. And as we saw in instruments, the determining factors were the strength of the magnets, the size of the conductor, and the speed or the rate of cutting. But every time, as we come through the midway point, look, we're producing no voltage, but then we're producing positive on one side, negative on the other, AC current. Because of the fact that once the circuit is established, current will flow in both directions instantly. It means that AC is very, very suitable for transmission over long distances. That's why AC is what's on the power lines that march across the country. If you had to try and do that with DC, you'd need another generating substation every other pylon. Remember, it doesn't matter whether we turn a magnet inside the coil, or we turn a coil around a magnet, inside a magnet, or indeed with windings of electromagnets inside another bunch of windings. In this case, we are producing, every time that goes past the pole, every time it goes past, it's generating a pulse of AC electricity. If we were then to look at the AC electricity on an oscilloscope, we'd see that the three phases come out like that. And basically on those coils, each of those is connected. Do you remember the back of the alternator the American guy was talking about? One end of it, the windings are connected, star connected together, and the other end is the three outputs. Okay. Calculating the frequency is fairly straightforward. Frequency is equal to RPM times pole pairs over 60. The over 60 bit is just to get us from revolutions per minute to frequency per second, which is what we're after. So really, RPM time pole pairs over 60. For example, if we had 3 pole pairs turning at 4,000 RPM, what would be the frequency? What you got, Jim? You got your calculator out?
200.
200.
Yes.
So 4,000 times 3 over 60 gives us 200 hertz. Yeah? The examiner might well change the sequence around though and ask you how many pole pairs would you require with a generator at 6,000 RPM? How many is it? 4? Why is it 4, John? Because that's the answer to the question bank. Good enough for me, fella. Okay. But remember, the formula to get it is RPM times pole pairs over 60. And if you've got any two pieces of that information, you can get the third, can't you? Okay. This is a typical brushless self-excited generator. AC generator. Now what we've got is a pair of small permanent magnets in there, which is what's going to give us some residual magnetism for the initial excitation current. Once we've got that going, the DC on the other end of the shaft will produce the current that we require for the main field windings. Okay, this is a sort of sketch diagram of what you saw on the animation there, where you've got AC on one end of the shaft and a small DC generator on the other end of the shaft. So a self-excited system. AC generators then, okay. They are more flexible in use than using DC generators. You can do things more easily with them. They're also lighter than DC generators. They have a better power to weight ratio. It's very easy to change the voltage using transformers, so they're versatile. It's also fairly straightforward to convert AC to DC if that's required. Brushless, they tend to use constant contact slip rings rather than carbon brushes and commutators, so less maintenance. They're working for you at lower RPM than DC generators would be, so that's a good thing. Most light piston aircraft use alternators, which is where we're generating AC electricity and then converting to DC. Through a rectifier. We'll look at some of that in a bit. Some small gas turbine aircraft will use a DC starter generator. We touched on that. Again, DC starter motor to start the thing up from the battery or external power, and then as soon as it's running it becomes a generator and it's producing DC. In that case, if you want AC, you've got to convert it through an inverter. So DC to AC through an inverter. Pays your money, takes your choice, I suppose. Now, we talked about the star connection business. Star connection is where one end is connected. One end is connected to the three lines, and then the other is the loads. Yeah, so if you like, that was the back of the alternator on the video. You've got a return line as well, but your three loads are on your green, your red, and your blue circuits there. Now then, phase voltage is the voltage of a single phase above the timeline. So phase voltage there would refer to that, and line voltage would be with any two pairs, any two lines. So if we were using two phases of electricity, either A and B or A and C in this case, then that would be our line voltage. We use three-phase because it's smoother in operation. Smoother in operation than single or two or four-phase. Three-phase is the common standard for everything. Okay. We're doing well on time, so let's take another break and come back in at